Welcome to this explainer. Today, we're unpacking the invisible, life-giving shield that completely envelops our planet, the Earth's atmosphere. You know, most of the time, we don't even give the air around us a second thought unless the wind is absolutely howling. But today, we're going to zoom in on what it actually is, what it's made of, and exactly how it's structured to, well, keep us all alive. Let's dive right in. To kick things off, let's just pose a pretty massive question. Can you imagine what would happen to us if there was no ozone in the atmosphere? It's a really great way to put things into perspective, right? Think about it. We eat a few times a day, we might drink water every couple of hours, but we breathe every few seconds. Without the atmosphere, and specifically protective layers like ozone, survival isn't just difficult, it's completely impossible. So, let's establish exactly what we're talking about here. The atmosphere is literally defined as a mixture of different gases that envelopes the Earth. But here is a truly mind-blowing fact about the sky above us. 99% of the atmosphere's total mass is confined to just the first 32 kilometers from the surface. It looks infinite when you look up, but in planetary terms, it's actually an incredibly thin, fragile layer of life support. Here is our roadmap for unpacking this puzzle from the bottom up. 1. Composition of gases and vapor. 2. Composition of dust particles. 3. Structure of the lower layers. And 4. Structure of the upper layers. All right, part 1. Composition, gases, and vapor. Let's start with the ingredients. It's absolutely crucial to understand that the air isn't just one static, uniform mix everywhere. Think of it as a dynamic recipe. For example, at 120 kilometers up, life-giving oxygen becomes almost negligible. If you travel up that high, oxygen is practically gone. Meanwhile, carbon dioxide and water vapor fade out much earlier. They're really only found up to about 90 kilometers from the surface. Now, water vapor is a total shapeshifter depending on where you stand. In the warm, wet tropics, it can actually account for up to 4% of the air by volume. But move out to dry deserts or freezing polar regions, and it plummets to less than 1%. It essentially acts like a giant invisible thermal blanket, absorbing solar energy and preserving the Earth's radiated heat to keep our climate perfectly comfortable. Then we've got carbon dioxide. It might be a tiny fraction of the atmosphere by volume, but meteorologically speaking, it is a heavy hitter. Why? Because it's transparent to incoming solar radiation, meaning it lets the sun's heat right in, but it's opaque to outgoing terrestrial radiation. It actively traps the heat trying to leave Earth. That dynamic right there makes it largely responsible for the greenhouse effect. And as we know, its volume has been rising lately, mainly due to the burning of fossil fuels, which is bumping up global temperatures. Moving right along to part 2, composition, dust particles. Okay, stepping beyond the invisible gases, it's pretty fascinating to realize the air naturally holds enough capacity to keep solid particles constantly afloat. And just look at where this stuff comes from. We're talking sea salts, fine soils, smoke, soot, ash, pollen, and amazingly, even disintegrated particles of meteors. These are usually heavily concentrated in the lower layers, but strong convectional air currents can actually sweep them up to some massive heights. Now, you might be wondering, why do we even care about microscopic dust floating around? Well, it all comes down to a fancy geographer term, hygroscopic nuclei. Basically, dust and salt particles act as tiny little anchors. Water vapor needs something to condense around to produce clouds, and these particles do exactly that. So without these tiny, seemingly annoying specks of dust and salt, water vapor wouldn't have anything to latch onto, which means no clouds and no rain. All right, section 3, structure, the lower layers. Let's get into how this is all built. Now that we know exactly what's floating around in the sky, let's start ascending through the specific layers where all these elements reside. Mapping out the atmosphere vertically, we can actually divide this vast column into 5 distinct layers, and the borders are defined entirely by temperature conditions. Let's climb from the ground up, starting with the zone we all inhabit. We start right here at the absolute bottom in the troposphere. This lowermost layer has an average height of roughly 13 kilometers, and it is hands down the most important layer for all biological activity. Why is that? Because this is where literally all changes in climate and weather take place. All those dust particles and that water vapor we just talked about, this is their home. But here's a really fun quirk about the troposphere. It actually has a totally uneven thickness. It's only about 8 kilometers thick near the cold poles, but it stretches out to a massive 18 kilometers at the equator. This bulge happens because strong convectional currents transport heat to incredibly great heights in warmer regions. Also, as you climb through this layer, the temperature actively drops by 1 degree Celsius for every 165 meters you go up. Right before we cross into the next layer, we hit a literal atmospheric ceiling called the tropopause. This boundary zone separates the troposphere below from the stratosphere above. What's totally unique here is that the temperature suddenly stops dropping and becomes nearly constant. And it gets intensely cold. The air temperature at the tropopause hits about -80 degrees Celsius over the equator and -45 degrees Celsius over the poles. Pushing up through that ceiling, we build right into the stratosphere, which extends to a height of 50 kilometers. Remember that existential question from the very beginning about life without ozone? Well, this is where it lives. The stratosphere acts as our ultimate planetary filter, absorbing intense, harmful ultraviolet radiation from the sun to shield absolutely all life down on Earth. Which brings us to Section 4, Structure, the upper layers. Okay, leaving the comfortable biological safe zones of the troposphere and stratosphere behind, we are now entering the extreme upper layers. First up is the mesosphere, which extends up to 80 kilometers. Out here, the temperature starts decreasing with altitude once again. By the time you hit its upper limit, a boundary known as the mesopause, the temperature plummets to an incredibly freezing -100 degrees Celsius. Keep going even higher and we enter the thermosphere. Nested right at the bottom of this layer, between 80 and 400 kilometers up, is the ionosphere. It's packed with electrically charged particles called ions. This is a brilliant example of how our atmosphere actually facilitates modern tech. The ionosphere literally acts as a mirror, reflecting our transmitted radio waves right back down to Earth. And notice the sudden shift here. The temperature actually starts increasing with height again. Finally, we reach the exosphere, the absolute highest top floor layer of the atmosphere, sitting right above the thermosphere. Whatever gaseous contents exist out here are extremely rarefied, meaning they are incredibly thin and spread out. There's no hard physical border where Earth officially ends. Instead, this layer just gradually and quietly merges into the vast, empty vacuum of outer space. So even though our vertical journey just took us hundreds of kilometers up to the very edge of space, it's really important to ground ourselves with this specific idea. Geographers generally focus most of their attention on just the first two layers, the troposphere and the stratosphere. Why? Because that is exactly where the weather, the climate, the oxygen, and the protective ozone that directly influence day-to-day human life actually exist and operate. To wrap up this explainer, I want to leave you with a bit of a planetary puzzle to think about. We've seen how perfectly structured the atmosphere is and how delicate ingredients like carbon dioxide and water vapor manage our planet's heat. If the volume of these variable elements continues to change, like the rising carbon dioxide levels we discussed, how might that dynamically shift and redefine the very atmospheric layers we just explored, the layers we literally rely on for our survival? It's a massive, real-time experiment happening right above our heads. Thanks so much for exploring the sky with me today.